Every single day, we walk into buildings, we drive over bridges, and we go through tunnels. And we don't even think about it. We just trust that they'll hold. But you know what? That trust isn't just blind faith. It's engineered very carefully through a whole world of constant, rigorous testing. These tests are like the invisible guardians that keep us safe.
So that leads to the big question, right? How do we actually know? How can we be so sure that these massive, heavy structures aren't going to fail? Well, the answer is a really fascinating journey into the science of structural engineering. And believe it or not, it starts way before a building ever gets off the ground.
Okay, so let's get into it. The very first line of defense happens when the materials are still fresh, and for a huge number of structures, that means one thing: concrete. Before it hardens into the solid backbone of a building, it has to have just the right consistency.
Now, that perfect consistency has a name. It's called workability, and it is absolutely crucial. You can think of it like cake batter. If the batter's too thick, you can't get it into all the corners of the pan. But if it's too runny, all the good stuff just sinks to the bottom. Same with concrete. If the workability is off, you get air pockets, weak spots, and it's not mixed evenly. That's a recipe for disaster.
So how do engineers check this right there on a busy construction site? With a brilliantly simple method called the slump test. Seriously, they just fill this special cone with fresh concrete in 3 layers, poke each layer with a rod to get the air out, and then they carefully lift the cone straight up. The amount the wet concrete slumps down tells them everything they need to know about its workability. Simple, right?
And here's the equipment itself. It's not some complicated computer. It's literally just a metal cone and a rod. This super simple, on-the-spot check is one of the most important quality control tests in the entire construction industry. It makes sure the concrete going into the structure is exactly what it needs to be to get strong and last. But, a good mix is only the beginning. Once that concrete is hardened, or a brick wall is built, the next question is pretty obvious. Just how strong is this thing? And that's where we get into testing the finished product.
And there are basically 2 main ways to go about this. First, you've got destructive testing. The name says it all, really. You take a sample of the material and you break it. You push it to its absolute limit to find out its ultimate strength. Then there's the other approach, non-destructive testing, or NDT. Think of this like a doctor's checkup for a building. You assess its health without actually hurting it.
And this is what brute force science looks like. To find the absolute limit of a wall, engineers will literally build a sample in a lab, stick it in a giant press, and just squeeze and squeeze until it shatters. Yeah, it's messy, but it gives them the exact data they need on how much squeezing force a wall like this can take before it gives up.
But it's not all about being crushed. Strength is also about bending. What you're seeing here is a concrete beam in what's called a flexural strength test. They're basically measuring its ability to resist bending forces. This perfectly simulates the kind of stress a beam in a floor or a bridge has to deal with every day, and it tells engineers exactly how much it can flex before it cracks.
Okay, so obviously you can't go around crushing a wall in a finished skyscraper. That would be bad. This is why non-destructive testing is so important. And this quote really hits the nail on the head. You can test an actual in-use structure and then come back years later to test the very same spot to see how it's holding up over time.
And the tools they use for this are just incredible. On the one hand, you got something pretty simple like the rebound hammer. It basically just taps the concrete to measure how hard the surface is, which gives you a good idea of its overall strength. But to see inside the concrete, for that you need something that works kind of like a medical ultrasound. That's the ultrasonic pulse velocity meter. It shoots sound waves right through the material, and by clocking how fast they travel, it can find hidden cracks or voids without leaving so much as a scratch.
And for older materials, like brick and stone, the techniques get even more clever. The flat jack test involves cutting a tiny slot in the mortar, slipping in a thin metal jack, and pumping it up to measure the stress that's already inside the wall. The push-shear test is exactly what it sounds like. They push on a single brick to see how strong the mortar is. It's like performing surgery to collect data.
So, all this testing gives us a ton of numbers, a lot of data. But what if you could actually see the invisible forces moving around inside a material? Well, in the lab you can. There's this amazing technique called photoelasticity. Here's how it works. Engineers make a model of a part out of a special transparent plastic. Then they shine polarized light through it while applying pressure. The stress inside the model literally bends the light, creating these unbelievable, colorful patterns.
And this is the result. How beautiful is that? These colorful bands are called fringes. And here's the key. Wherever you see those fringes packed really tightly together, that's where the stress is most concentrated. An engineer can look at this one image and immediately see the potential weak spots in a design, long before a single piece of steel is ever cut. It's incredible.
And here's the setup that makes all that magic happen. The photoelastic bench. You've got your light source, a couple of polarizers to filter that light, a frame to squeeze or pull on the model, and then an analyzer to see the results. It's just a powerful, powerful tool for seeing how our structures really handle force.
Okay, so that's amazing for clear plastic models. But what about the real world? How do we understand what's going on inside something totally opaque and super strong, like steel?
Well, the answer lies in a wonderful property called ductility, and you can see it perfectly in the stress-strain curve for steel. So as you apply force, that's the stress, the steel starts to stretch, that's the strain. But look at this long, flat section right here. This is where the steel yields. It's deforming and stretching a huge amount before it actually breaks. And that is a critical, life-saving feature. It means a steel structure will sag and bend and give all sorts of visible warnings long before it ever just snaps.
So, we've looked at tests for wet concrete, tests that literally crush walls, and even tests that let us see invisible forces. But this all comes down to one simple question: why does any of this matter?
It matters because every single one of these tests, from that little slump cone on a construction site to a complex photoelastic analysis in a lab, is another link in a long chain of safety. This constant testing doesn't just prevent disasters. It lets architects dream bigger, it lets engineers build smarter, and it lets all of us walk around with confidence in the world we've built around us.
Right now, all this testing is basically our way of asking our structures how they're holding up. But it does leave us with a pretty cool question for the future. As we develop things like self-healing concrete and steel with sensors baked right in, will our buildings one day be able to just tell us how they're doing all by themselves?